Welcome to the third lecture on hardware security. So recall that in the previous two lectures, we discussed the fundamentals of cryptography and security, and then we discussed the Intel SGX design in great detail. So now we want to kind of conclude the chapter. So we'll finish whatever we have of the SGX part, and we will talk about side channel attacks. So let's come to creating and managing an enclave. Recall that enclave is a secure region where an application runs. So it's normally created at boot time. So what you do is you take your entire memory space and you partition it into two parts. So you have a regular or unsecure region. That's what it's called. It's not non-secure, it's unsecure. And then you have a secure region which is reserved for your secure programs. So in general, this was SGX V1, which was there in the Intel processors, the 9th and 10th generation processors. But now, of course, the size of the secure region is much larger, and they have also done away with many of the slower optimizations like the Merkle tree and so on. But let's look at the classical enclave creation mechanism. So here what you do is you partition this reserved memory into two subparts. One part stores the metadata for the secure region, and the other one stores the secure data and secure instructions. So I'm counting instructions as data. So in the older version, the size of this processor reserved memory was 128 MB and the usable space was only 92 megabytes. So that really limited the size of the enclave. And furthermore, new instructions were added to the ISA such that an enclave can be created, deleted, restored, you can go into an enclave, you can come out, so on and so forth. So a typical SGX program had the portions that used to execute in an unsecure fashion. And then it had portions that it used to execute in a secure fashion, so on and so forth. So you had a way to come in and you had a way to come out. So let's first look at setting up the enclave. So we look at three instructions: eCreate, eAdd, and eInit. So eCreate would essentially initialize the data structures corresponding to the enclave, and all of those data structures would be stored in the metadata area. So what SGX does is that it literally partitions the physical address space as well as the virtual address space between the secure and non-secure regions. Essentially, given an address, be it physical or virtual, you know whether it's in the unsecure region or in the secure region. And also, the nice thing is that you also know whether it's a secure page or unsecure page, and these pages are treated differently. But that said and done, the paging hardware, etc., is all managed by the OS. But we'll see there are some small things that ensure the security, but the OS primarily manages the page tables and the TLBs, right? So even though it is not trusted, but we will see a little bit of additional hardware can ensure that the OS cannot actually do any malicious modifications over here. Then we come to the eAdd, enclave add instruction, which basically adds the code and data of the program, the secure program, to the secure enclave. So what it does is that it copies data from the unsecure part to the secure part. That it does. So it will copy the data into the secured pages and then initialize the enclave. Initializing the enclave is not as simple as you think, because before running the enclave, you will have to ensure that everything that is running is secure. So this is where we'll compute a hash. The hash is known as a measurement. Digitally sign the measurement to ensure that the processor is indeed generating the measurement or the measurement has not been tampered with. Then we could also use the help of another sister enclave known as the quoting enclave to sign the measurement. Then we send it for verification, right? So this can be done verified locally, or you can send it to a remote machine. And only when the verification comes, of course, appropriately cryptographically signed, we can then launch the enclave, right? So that's the overall idea. That's how it works. that we create an instruction, we add pages to it, and we initialize it. So in terms of memory management, as we said, this is by far the most important when it comes to security. The OS manages the page tables, it manages the TLBs, it manages everything. The OS can of course deliberately induce TLB and page faults by regularly clearing them. So this will give it the page access sequence. So once you see the page access sequence, you would think about it, this is a source of information, right? So this is a source of information for us in the sense we are getting the page access sequence. But one nice thing that SGX does is that this, it's not a perfect source of information. So what it does is that whenever there is a page fault, normally you will also give the address at which there was a page fault. But in the case of a secure page, what you do is that you only give the page number, let's say the 12 bits that correspond to the offset, they are all zeroed out. So this, in a sense, stops the flow of information, at least to some extent. In a sense, you don't get the exact byte address or word address within the page that actually caused the fault. So many such information leaks are actually stopped. So now the question is, how do you stop the OS from redirecting writes to the non-secure or unsecure region? Well, so what the OS can do is that if you want to write to a secure page, then it can simply change the mapping of the secure page such that if the program is writing to the secure page, instead of going to the real address, it can actually go to a fake address which the OS can read. Why is this possible? Because the TLB mapping and the page table mapping is there in the OS's hands. And this is why it is possible. But here again, the designers of SGX have done something quite smart. So whenever you try to kind of add a new TLB mapping or you try to populate the TLB from the page table, if it's a secure page, the OS will not, the hardware, the dedicated SGX hardware will not allow you to do it. What it will instead do is that in secure memory, it maintains an inverted page table, which means given a physical address, it kind of points to all the virtual addresses that point to it. And all of these should be secure or should be validated in some sense. So what we do is that the moment we want to access something, we go to the virtual address and we check the IPT. If the IPT has an entry but the OS is saying that this is some other entry, it means that the OS has tampered with the mapping, which is not allowed, right? So this is where the inverted page table comes in very handy. Furthermore, if we have a secure physical address, it gives us a list of all the virtual addresses which hold data for this physical address. So this is again a way of checking the security of the program. But if you were to ask me the takeaway point, the takeaway point is that the OS cannot arbitrarily assign a mapping, because every time a mapping for a secure page enters the TLB, it is validated using the IPT to ensure that it is what it should be, it is not something else. And the IPT is a copy of the page table which is kept in the metadata region. So the enclave add instruction adds code and data to the secure enclave and copies the secure pages. So what we do is that after all the instructions have been added, the IPT is created. But before you launch the enclave, you just check the validity of the IPT, which is not very hard to do. So the idea basically is that you just go through your list of pages. Any secure page in the IPT should not be pointing to a non-secure memory region, page in a region of the memory that is not secure, or something which is accessible to the OS that should not be happening. Furthermore, how do we ensure that the IPT is continuously updated? Well, that is easy. So we allow the software to manage the page table, no problem. But the page table as it is not usable. Mappings have to come to the TLB and these mappings are monitored. So monitored means what? Any time that there is a change in the mapping, a copy is sent to the IPT. Right? So this ensures that at all points of time, whatever change happens to the TLB, the IPT gets to know, and it sees that no illegal mapping is created in the sense that a secure page, a secure virtual page is not mapped to an unsecure physical page. Let the OS maintain the page table, no problem, because the page table as it is, the processor doesn't directly use, it uses it via the TLB only, right? And the thing is that the OS can furthermore move out pages from the secure region to the unsecure region, albeit in an encrypted form. But here again, the ASIF guarantees, which is authenticity, confidentiality, integrity, and freshness guarantees, are maintained, which basically means that any time that we would like to read the data in this page, it needs to come back to the secure region, and then all the regular checks happen. SGX additionally has something called an eviction tree or a waiting tree, which is again done by the hardware, right? Managed by the hardware. So what happens is in the earlier version of SGX, now of course this size is much more, the number of usable pages, etc., everything had to fit within 92 megabytes. So the moment that you wanted to use more memory, the hardware will automatically move this with OS support to another region of the unsecure memory. So the idea was that again, if any of these pages are required, they would come back. Similar to a Merkle tree, an eviction tree was maintained, again for the integrity and freshness of all the data, which is moved from the secure to the unsecure region. Right? So that is the broad idea over here. Same idea of the Merkle tree, albeit in a somewhat different setting. So let's now look at the way that a secure program runs. As I said, there is an unsecure region, there is a secure region, unsecure, secure, so on and so forth. So let's first look at what happens if an external interrupt comes. So the code is running in the secure context. Then we have what is called an asynchronous enclave exit, where basically the context of the secure program needs to be stored. So context would include the register state, the state of the functional units, all of that. So when all of that context is stored, that cannot be stored in an area that is accessible to the OS, right? So that cannot be stored within the process control block as is typically done. Instead, something like that has to be provided by the SGX hardware in its metadata region to store the secure context. That is done. So every secure program that kind of needs to context switch, its context is stored in a secure region within the overall metadata. Right, so that is that additional 28 plus 8, 36 MB in the earlier version of SGX. Then of course we flush the TLB. Why do we flush the TLB? Because we don't want any of the mappings, which means the secure page mappings, accessible to the OS. Right, it should not be accessible. So the TLB in this case has to be flushed, and this is a significant source of overheads. Then we enter the enclave, then we enter the OS and we do our job and we come back. Many a time what happens is that we would like to do a bunch of actions in unsecure part, process a secure function like a cryptographic function and come back. So to enter the enclave, we have an EENTER instruction, which is wrapped inside a secure function called an ECALL. So you can think of ECALL as an entry call, like getting into the enclave kind of call. So this is a regular context switch insofar as the OS is concerned, because it is essentially turning on the secure mode and you are pretty much going into a new memory area executing its code, and then you are coming back. So you are calling a secure function. And again, when you exit, this is again treated as a special event called an OCALL, where you would like to come back to the unsecure region, right? So all the arguments, and so some arguments, there is some data transfer that is allowed, of course, in a highly regulated fashion. But the most important thing is that we flush the TLB, right? So the TLB is flushed, which is something that does not happen while entry, because while entry we are entering the secure region. Say we would still like to keep the same mappings because we would like to read or write, whatever we had earlier, we would like to access that. But anything new that is created, that is something that the secure region should only have access to, and the unsecure region should not have access to. That is why the TLB is flushed, and this is a source of significant overlaps. Now, how do I remove an enclave? Well, we have an remove instruction, which is used to break down or tear down an enclave. So, which means that all the state is removed in the memory and disk, which includes zeroing out pages. So, all of that is done. Furthermore, we cannot invoke any system calls or do any other privileged actions in a secure mode. That is basically because the OS will get to see what you are doing. It will get to take a look at your state. So any such action which an enclave does not allow, what we do is we exit the enclave, we do an OCALL, right? Or we send and then we kind of start a proxy thread which will execute the system call, and then we take its data and we come back to the enclave using an eCall, and then we resume from there. So the idea is that in any SGX application, we'll have a bunch of these OCalls and eCalls, mainly because a lot of actions are not possible, are not doable in SGX mode, right? So that's the reason it is important to sort of come out, either do the action yourself or give it to another thread to do it on your behalf, collect the results and come back in. So now that we have discussed the software aspect of SGX, let us discuss one more idea. It's called Oblivious RAM, it's also called ORAM. So ORAM is a theoretical concept by and large, but it is seeing a lot of practical application where the idea is quite simple, that the memory address stream. So what happens the moment there's an LLC miss, a memory address is sent to the main memory, then the main memory does a read or write. In the case of a write, it actually returns data. All right. In the case of a read, it returns data. In the case of a write, it may or may not return an acknowledgement, depending on the protocol. Most of the time, it doesn't. So the memory controller would return one, but that is seated in the CPU. But the addresses are visible, and that could be a significant source of information. So there is a fair amount of work which leaks cryptographic secrets and keys from the address sequence. So a simple idea that you may want to argue is, why not encrypt the address? It is just that then we need some chip on the DRAM side to decrypt it, key management and so on. And the DRAM industry for decades has resisted all such kind of change, right? It has totally resisted this. So the only idea to still kind of obfuscate the sequence of addresses is to follow two strategies. These are expensive, very expensive, and the original DRAM paper had huge overheads. So the idea was that you keep some sort of a mapping within the CPU, where what you do is the moment you access some location in main memory, you kind of migrate that to another location. So this is like, some sort of a further virtualization of physical memory, where you would have this massive lookup table inside the CPU, or perhaps some of it overflowing to the DRAM, where the idea would be this would be the physical address that would go, or let's call it the logical address, that's typically what it's called. And what comes out is the physical address. So what goes in is the logical address, what comes out is the physical address. So previously, your job of the TLB and the page table is to convert from VA to LA. And then had we not had ORAM, the logical address would be the same as the physical address. But in the case of ORAM, we will further kind of obfuscate it and kind of map it somewhere else. And the moment we have done that, our data in the DRAM would also be jumping between locations. We access it here, then we kind of copy it and put it here. Next time we access it from here. Then we copy it, put it here. Next time we access it from here. So this, of course, confuses the attacker somewhat. Also, the other idea is that if we want to access one location, we actually access k locations. And one of those k locations contains the actual data. This further confuses. So, and which location stores the actual data is there within the CPU, which is within the TCP. So, with both these strategies, it has been shown that we can somewhat create an oblivious RAM where it will become very hard for an attacker to actually extract secrets from the memory address stream. But this is very slow, it has significant overheads. So, what you do is that you first discard the simplest or the most naive solution, which is that for every memory access, you access the entire memory. If you do that, it will work. If you access the entire memory for every memory access, then the adversary has no way of knowing which location you actually wanted to access. So this is secure. But the point with this approach is that its overhead is very, very, very high. Right? So basically accessing all the locations to access just one is not a good idea. Instead, we should, so this idea is permutation, where you permute. And this idea of accessing more locations and kind of, let's say in the case of a read, choosing only one of the values, this is known as redundancy. So any combination of permutation and redundancy would do our job. So a new approach was designed a couple of years ago known as path ORAM, which is a far more efficient version of ORAM, where if we consider that we have capital N memory blocks, then of course we'll have N mapped addresses, and the local cache or the stash, that's what it's called, is where most of the magic happens. So what we do is that we kind of divide our memory space into buckets, where each bucket has B blocks. Then we create a tree of these buckets with 2 raised to the power L leaves, right? So pretty much, if you think about it, we are assuming that we have L plus 1 levels, where a level is like this, that let's say if I were to just consider this tree, I would say it has 1 level. So we have 2 leaves. So we have L plus 1 levels, and L is log n to the fixed. So this is a standard construction of a tree. So what we do is that if we want to, let's say, read a block in the kth leaf, right, which is the kth bucket, then we will return the contents of all the blocks from the root to the kth leaf. So basically when we read, we will go through the tree and then we will just go down this path. We will read the contents of all the buckets and return all of it. Then what will happen is that the data for any single address could be present in basically in any block in the path, right? So if this is the path, then basically this could be present anywhere. Okay, so basically if I consider an address A, right, so we'll just see what postmap A is in a second, but postmap is essentially the position map. So it's essentially telling you that for an address A, which leaf am I referring to? So then you kind of look at the path. So this, as you can see, this is PK. PK means this is the kth leaf and this is the path to the kth leaf. So this is capital PK. So what I do is given an address, it gives me the number of the postmap A, gives me the number of the leaf. And then what I do is I find the path from the root to that leaf. I read all the blocks on the path and my actual block is there somewhere in this path. So it is important to go through this argument several times and also read the relevant part of the book to kind of gain a better understanding or a more superlative understanding of what is it that I'm trying to say. But the key point is that given an address, you first map it to a leaf. Given a leaf, you find the path from the root. Given the path, you find all the buckets, and from there you find all the blocks. And basically, in any one block, these are all the blocks in any one block, our data is there. So let's look at a few more definitions. So we have already seen the definition of post map. So what that does is that takes an address and maps it to a given leaf of given leaf of the tree or given block. So the blocks themselves are arranged as a tree, as you can see. The tree has 2 raised to the power L leaves at this point. So it has L plus 1 levels, where the definition is that if you have one level, you have 2 nodes at the leaf level. So there are a total of log n to the base 2 levels. That's easy to see. So what is the main aim of doing this? The main aim is to define a function called get cousins, right? So that's the main aim, where we will get, W addresses as the output. So let's understand what is there in this get cousins. So the idea is that you want to find, you want to find a set W. For every address that is a part of the set W, these two conditions have to hold true. So essentially the output is a set of addresses which are part of a set called W. And there you want something to hold true. What is it that you want to hold true? So what you want is that if you consider the kth leaf and consider the path pk, which is the path from the root to the kth leaf, this is the path pk. Then what you do is that you consider the lth node in this path, right? So if I, let's say, give you k and l, then what you do is that you look at pk, the path pk, find the lth node, and that should be equal to, for a given address, you find its post map, find its path, and in this path, as you can see, in the lth node, right, this is there in this path, right? So post map al, this is actually the same bucket over here. And furthermore, this address has to be present in an on-chip cache known as the stash. So there are essentially 2 requirements for a cousin. It is basically all the addresses that are there in the stash, and that for a given k and l, essentially the path has to diverge only at the lth point or at some point after that, but not before that. So this basically means that everything within the subtree will be considered for the first condition. For the second condition, we will essentially pick out the subset that is a part of the stash, and that would comprise the set W. So the get cousins function basically finds, well, first it finds a subtree, right? And then what it does is within the subtree, it just filters out those nodes that are a part of the stash. So now if I look at the algorithm in its full detail, it's not very hard to understand. So let OP be the operation, be it a read or a write. Let A be the address. And if this operation is a write, let new data be the data that I'm writing to. So the function that I want to do is I want to define a function called access, where I'm either reading or writing to a given address. And if I'm writing, then I'll write something. If I'm reading, I will return something. So what I do is I access the post map, and then I figure out basically where is this there in the position map, in which leaf. So this essentially gives me the leaf address of the post map. Essentially it tells me where is it over here, right? So this is what post map is, this is what the post variable does. Then what I do is I randomly do the permutation, in the sense I say that, look, henceforth, I will set a new location for the address A, which will be one of the leaves from 0 to n minus 1. Some place I will put it, all right? And basically, one out of those n leaves I will put it. So this basically means that if you have accessed something at some location, the next time you go to access, it will be there in a different location. So this permutation will be done. So we will compute it. Then what we do is that we look at the path from the root of the tree to the leaf. So from the position that I computed to the root, I find all the nodes. Then in all the nodes, all the blocks that I find, which means blocks and the contents of all the blocks, everything, all of that I add to the stash. So stash is an on-chip cache. So as I said, our algorithm is such that the data can be found in any block that is on the path. So what I do is, the moment I access something, then I go and I pick everything on the path and I put it in the stash. Then I implement the read or write, whatsoever may be the operation. If it's a write, then what I will do is I will add, so in all cases I'll add it to the stash. So as you can see, it is added to the stash right here. If it's being read, I will read it. If it's being written, I will write to it. So let us now look at the second part of the algorithm where we do the permutation. So what we do is we have a for loop where we move up the levels from level L to level 0, which is still the root. So the idea is simple. At every point, we consider this location pos, which was defined here, right, as the position, original position, leaf position of the address. Then what we do is we find the path, right, where this being the root and this being what we have mapped pos to, right? So this being pos, actually the position. So once we have done that and we have found the path, and let's say the level is L, then we kind of look at the cousins. So the cousins would be essentially every node here, which is a part of the stash. So then let this set be W. What we do is we trim W. Trimming W basically means that we only keep that many entries that can fit within a block, right? So that is what we do. We trim it. And then for every address within W, what we do is that we create a new block, because as you can see, the size of W is one block. So because it has been trimmed, so we create a new block and we kind of replace this entry here, which is P pos L. As you can see, it's this entry over here in the tree. We replace it with the address in every address. So it's for all A dash, where A dash is an address. For every such address, we are adding the address as well as the data. And where will you find the data? You will find the data in the stash, right? And you're guaranteed to find it because that is the way get cousins is defined. So any A dash comma S A dash is something that is there in the stash. This is the address, this is the data. Both we will add and we will replace this bucket over here. So this is essentially showing you the permutations, the way we are moving things around. And finally, once this has been moved here, we can remove these entries from the stash. So this ensures that even the size of the stash is limited. So what's the idea? We read the path, we locate the node L here, we find the cousins, we then pick a subset of them that will fit in one block, create a new block over here by kind of replacing the earlier block. And finally, whatever we put in here, we remove that from the stash. So as I said, this is just a way of mangling data around and kind of permuting. So there is a formal proof for why this works, but let's not get into that. It's well beyond the scope of our current discussion. But this should be enough to understand that this is the path ORAM algorithm, which we have seen in full glory pretty much. It is impractical because for every memory access, we will have to do this, right? That is why it is quite impractical. Even if you argue that this is a far more efficient version of the ORAM protocol. In spite of that, it is quite impractical. But that said and done, there are improvements and approximations to this. This is a hot area of research. So let's now come to the last part, which is side channel attacks, where the idea is that you don't directly take the data, but you look at some other artifact or aspect of the execution, and from there you infer some data via which it's possible to infer, let's say, the value of a private key. So one of the culprits that is often implicated in any side channel attack is the high resolution timer, which is, a nanosecond level timer that most processors have, and it's needed. Why is it needed? Well, you need it for device drivers, particularly high throughput network device drivers, computer games, and so on. So what happens is that this is the basic principle, that an L2 miss takes a long time to service because you go to main memory, so it takes hundreds of cycles. On the other hand, misses at the L1 level, etc., are very fast, right? So it's a very small penalty. So in either case, either it's an L2 miss or an L1 miss. In both cases, if you have high resolution timer, these small misses are detectable, and we can use the misinformation, or rather the timing information, which is a proxy for the misinformation, to figure out the addresses that your program is accessing. And the address sequence can give you some idea of the data that you are trying to predict. Because in many cases, depending upon the data, we would access one sequence of addresses, otherwise some other sequence of addresses. And it's further possible for an adversary to kind of actively increase the information content of the address sequence. So with that, we can exfiltrate credit card numbers, private keys, and everything. So the key question is that, looking at this hit miss behavior and this address sequences and timings and so on, can we get some idea? Well, yes, if we can kind of finely craft a destructive interference in such a way that information is leaking out, right? There is information leakage. So let's now explain the space of side channel attacks. But before I do that, let me explain how the RSA algorithm works, the key part of it. So let C be the ciphertext and P be the plain text. Then the key approach that RSA follows is that C is P raised to the power E mod n, where E and n are very large prime numbers. And we can easily see that the plain text is C to the power D mod n, subject to E and D and n, mutually satisfying some properties. But the key point is that E, D, and n are very large prime numbers. And furthermore, we are relying on the fact that for integer factorization, we don't have a very efficient algorithm, a polynomial time algorithm as of now. So the entire proof relies on the hardness of that. So the key thing is that, how do you do this? How do you perform this operation? A naive approach would suggest that you kind of exponentiate this E times, which will take a long time, and then compute mod n. But a faster approach would be to kind of break it down in a tree and roughly use, log level steps. And that would basically mean, that's simple. It would rely basically on this fact that, let me perhaps explain with an example. 5% 3 is equal to 2. Similarly, let me write it twice. I'll tell you why. So what is 25% 3? So this is nothing but, because 25 is 5 square, 25% 3 is nothing but 2 into 2, 4% 3, which is actually 1. All right. Now let me maybe multiply this once again. What is 125% 3? So 125% 3 is basically, this number 2 cube percentage 3, which is 8% 3, which is 2. And you can readily verify that that is indeed the answer. So using this, of course, in this case, I used an example. I could have used algebra. My job would have been easier, but for understanding your job would have been tougher. But basically, the idea is that if I have computed something kind of partially and I multiply them, then the percentage threes also get multiplied with each other. So that's the reason there is no need to exponentiate. Instead, what we do is we look at this exponent e. If it's an odd number, then let's say the final output is z. So I'll temporarily compute z as z times x percentage n. This essentially converts it from odd to even in a certain sense, right? It's easy to prove. I'm not going through the proof. And then what I do is I divide e by 2, but we all know shift is more efficient than division. And then we kind of square x in a modular fashion. So essentially what you're trying to do is you're trying to create a bigger and bigger and bigger x, right? And such that it approaches this number in some sense. So you're essentially squaring it with itself, so it will approach it very quickly. So this is the broad idea. So let's not focus on the mathematical correctness that you can prove using the insight over here, but let's look at the security vulnerability or the side channel, which is far more important in this case. So in this case, what you do is that depending upon this exponent e, right, this test will sometimes be positive, sometimes be negative, because it all depends upon which bit of e you are seeing, right? So you are essentially traversing e bitwise, as you can see, because every time e percentage 2 is nothing but looking at the least significant bit of e, right? And so you are looking at the lowest bit of e, the e percentage 2. If the least significant bit is 1, you are doing this, else you are not doing it. Then you are again right shifting it, taking a look at the second least significant bit, which is now the least significant bit. Again looking at it, again looking at it. And whenever it is 1, this line is being executed. All that I need to do is that if I'm able to track accesses to this line, I can, lo and behold, figure out all the bits in exponent e, which is nothing but my key. And why would that be the case? Well, what I would do is I would run a timer and I would basically see how frequently this line is being accessed or what is the access pattern of this memory line. So let's say it's not being accessed, so there will be 0. If it's being accessed, it's 1, then 0, then 1, and so on. That is nothing but the bit pattern in E, which is nothing but E. So all that I have to do is I will take the memory, the cache line that corresponds to this. I will somehow evict it from the cache. We'll see how. And then I'll just see if this was accessed. Then I will try to do a dummy access and I can figure out whether the code accessed it or not. If it did, well, then I will register a hit, otherwise I'll register a miss. That information will tell me whether the code took this path or not. If it took this path, even though the code is a different process, I don't have access to it, I just know this address. All I have to do is somehow indirectly find if this address, the instruction address, that is not data address, instruction address, is it there in the caches or not? If it's there in the caches and I had last time cleared it, it means that it has been accessed. It means that the corresponding bit is 1. So all that I need to do as an adversary is essentially monitor accesses to this line in a very indirect fashion. So what I can do is that I can, if let's say it's a set associative cache and assume it's a 4-way set associative cache, then what I can do is I can fill all these 4 ways with my data. Then I run this RSA code. Say if the RSA code is accessing this this particular address, it's going to map to this set and you will have to evict some data, some line that I had added. Next time what I would do, I will pause this program. Again, I'll access all the lines in a set to see if my data is there or not. If it is there, it means that this access was not made. If it is not there, it means that this access was made and this access threw my line out. So of course, I'm making some simplistic assumptions here, but this is the broad idea that if, let's say, I don't find my data here, I can implicate this line that it was brought into the cache, which means that I have some idea what this bit is. If I run this experiment many times, I'll have a reasonably sure idea what the bits in the key are. So recall the fact that a side channel attack is not a direct attack. It's an indirect attack where I just observe some facets of the behavior. In this case, I am only trying to figure out hits and misses of my own process, but it's just so accurately crafted that in case there is a destructive interference, using my nanometer level timers, I'm able to detect it. And that is giving me an idea, and that idea is good enough. So what I can do is I can create a space of side channel attacks where I can have two kinds of attackers. In this case, the attacker is observing its own execution. It's not really modifying the execution of the secure process. So that would be self. Other would be where the attacker has some way of directly observing the execution of the secure process and making modifications to it, perhaps. So that would be the other class. So if I'm looking at myself, then I can look at the contention in functional units or in the memory system, or somehow, some way in which the secure program is affecting me. Based on how it is affecting me, I can figure out. So here again, there are not a lot of attacks in this space, so we have kept it empty. But if I'm observing the other program, I can look at the timing of different functions. For example, by the time that the algorithm takes, I can figure out roughly how many hits were there, how many misses were there. I can look at performance counters, that's a great source of data. I can look at the memory access patterns, because as we just discussed in the ORAM part, that the memory addresses that are sent to main memory are sent unencrypted. And that can give me some idea with regards to whether this line is being accessed or not. So all of these are logical in the sense that all of this is sensed by the program. That's logical. But then, of course, you can have physical where you can look at the power. So if, let's say, memory access is made here, the power signature will be different. You can look at electromagnetic radiation in the sense if, let's say, I am making memory accesses here, I'll generate different kinds of EM waves which can be detected. Temperature, well, not that much, but still to a certain extent. And anything else that I can externally measure, right? Including, looking at the memory address sequence. So this again, with a physical agent, I can put a probe on the memory bus and I can measure. So essentially using an artifact of the system, which is measurable, that is a side channel. And depending upon information that leaks out, what I can do is that I can collect a lot of this information, I can analyze it, and that can give me a fair idea with regards to what the exponent is. Then I will use a little bit of trial and error, and there are many successful attacks where I can figure out the exponent. So let's look at the prime probe attack, which is arguably one of the most popular attacks, and let's discuss it. So what the idea here is that the attacker thread accesses all the lines in the cache. There's a priming phase. Then you run the scheduler, you yield the processor for the victim process where the victim thread executes. The victim thread is a secure one, the one that's running RSA. So clearly, if it accesses a certain cache block, code or data, there will be a miss and something has to be fetched from the lower level because you have overwritten the full cache. Then what the attacker would do is that it would resume control. It would again try to access each and every cache line. For the lines that are not being touched, there will be a hit which can easily be detected using the timers. For the lines that have been touched, there will be a miss, so you can figure out what are those addresses. Because RSA has data dependent instruction accesses, right? Because of this single if statement check over here, you can see if this instruction right, which is just one instruction. That's all that it takes. If this instruction was fetched or not. If it was fetched, well, lo and behold, you have the ith bit of the key. So we can have a similar attack known as the flush reload attack. The basic principle remains the same always. So in this case, what you do is assume that you have a secure library such as OpenSSL. So in this case, the secure code is implemented in a library function. And the library function, the code itself is mapped to two different processes. Let's say process 1 and process 2. So in this case, code pages are shared, which is often the case with shared libraries. That you share your code pages to avoid redundancy in the memory system to use less space. So what the attacker can do is that it can flush a set of cache lines which correspond to the lines of the shared code. Again, you allow the victim to run for some time. Same idea, access the same set of lines, see if they are bad. So in this case, it's not a different process. Well, it is a different process, but you're sharing the code pages. So, right, but instead of accessing everything, you're just flushing a given set of cache lines. Right, the first one is priming. So priming was accessing, but in this case, you're flushing. Right, so flushing means removing. So what you do is that you take these things and you remove them, and then you wait for them to access. And because both of them are mapped into your virtual address space, you know that they are the same set of lines in the physical address space. So then you go there, you access them once again, then based on the hit miss times, you'll have a fairly accurate idea with regards to what was accessed. Again, this is a side channel, slightly different from prime and probe, but very similar. In the prime probe case, you access every line and see what happened to them. In this case, you flush them and you see what happened to them. These are not the only side channels. There are a bunch of many side channels. Essentially, wherever, let's look at the key ideas of a side channel. So first is that there has to be some data dependent access. Depending upon the data, your access pattern or some behavior, right? There has to be some data dependent behavior. If the behavior, be it an access pattern or anything else, is independent of the data, then it's not a side channel. And the other is that there has to be some contention, right? Somehow it should be possible by measuring the contention on shared resources to see if you are getting any hints or not. There is a lot of contention in a multi-threaded processor. You have contention on functional units, architectural structures, DRAM rows, and so on. So let's see. So a very common idea is this idea of this read disturbance, or what is called a row hammer attack. So what happens is that if you read a row repeatedly, you just keep on reading. Sooner or later, it will disturb the contents of the adjoining rows. All right. That is because, you will have a lot of charge, discharge, and so on. So adjoining rows will start losing charge and they may develop faults. And if they develop faults, then the error checking code, the ECC, will be invoked when it is accessed to fix them. That's going to take a higher latency. That is how you can figure out whether a line was accessed or not. So what an attacker can do is it can deliberately perturb a nearby row. After the victim accesses its row a sufficient number of times, the attacker's row will have a bit flip. So what you do is that if you have, let's say, this row that is being perturbed, this is the row that the attacker is using. This is the row that the victim is using. So what happens is that you keep on perturbing this row. So this row will start developing faults, but you kind of keep it below a threshold. But if the victim starts using its row, then you will breach the threshold and you will start seeing problems here. You will start seeing problems here. Then you can figure out that, look, I was below a threshold. So who took it above the threshold? It must have been the secure process or the victim process. Well, this means that it has been accessing a certain address which is there in this row, and you can get an idea of the access pattern. All of this is easily detectable by a high resolution timer. So as I said, there are many variants of this attack. This is known as a classical row hammer attack, where essentially you're hammering a row. What does hammering a row mean? What hammering a row means is that you are accessing it so many times that you are perturbing the values in nearby rows. So this can be a side channel, this can be a source of information. So as I said, this is not the only sacrosanct way of doing it. There are other methods which are simpler as well. For instance, you can, using the row hammer technique, you can create a fault in the victim process's row, which is supposedly secure, right? And then what you can do is you can see that the next time it is accessed, is the ECC hardware busy or not? If the ECC hardware is busy, that could give you a hint that a certain address has been accessed, and hence a certain bit has a certain value. Then there are a few more attacks. Again, they follow the same principle. This is the evict and time attack. So what happens is that in this case, the attacker deliberately evicts a few cache lines. You run the victim. Then you carefully measure how much time the victim took. See, if the victim is accessing the cache line, which is that, which is essentially this line over here, if this line is being accessed, it will suffer a miss and it will take more time. And then if we have, a cache miss counter, that would give us accurate information. Even otherwise, the time is a good proxy. So the victim will take more time. Again, you can infer the address sequence. So as I said, you can take a look at any other kind of data, performance counter data, page fault data, right, power, EM, temperature, everything. But broadly speaking, you have to have these two properties, that the side channel has to carry some information about the data. So there has to be some data dependent behavior. If for all kinds of data behavior is the same, it's not a side channel. The other thing is that whatever you're trying to measure should be affected by the secure process. In the sense, if you are trying to measure, let's say, your cache access times, the secure process should have modified your cache access times, right? Or if you are trying to measure the power, then the secure process should have somehow modified the power consumption. So basically, you need to see the effects of the data at the final output. So that is a side channel, and as I said, doesn't matter flush, reload, prime, probe, evict time. The reason I'm not going into a great amount of depth is because they all are different aspects of the same idea, which is either you access something, you wait for the victim to evict it such that the next time you access it, it is much slower because there is a miss. Or you evict something, you wait for the victim to add it, next time you access it, if the victim has indeed added it, you'll get a hit, right? So basically, it doesn't matter. You can either throw it out, which means evict it, flush it, wait for the victim again to add it, or you can add it and then you can wait for the victim to remove it, right? So someone has to add, someone has to remove, and that's how you will, by measuring the time, you can figure out whether it has happened or not. So then there is another class of attacks, Spectre, Meltdown, Foreshadow, etc., which are known as transient execution attacks. So this kind of attack is reasonably interesting. So consider this piece of code. So let's say that if a certain value is less than the threshold, we can get into this if statement. So normally what happens is that in an out of order processor, you predict branches. So because you predict branches, what happens is that you will speculatively execute, which means you'll speculatively access memory also. And then later on you will realize, oh, my, I had a branch prediction. So then you will flush all of those instructions. But the fact that you are accessing memory in a speculative path could be a side channel using again the same flush, reload, evict time, prime probe technique. So this is a side channel even during your speculative access. So all transient execution attacks are by and large based on this. So let's consider an example. So speculatively, you will find array to X, right? And then you will, so let's say the size of this is, it's an integer, it's 4 bytes. So you'll multiply this with 4 and you will add it to array 1 space. So essentially the address that you are accessing is this. So this address can easily be detected using the prime probe attack. If array 1 space is known, then array to X can be found out. Because why? Because you know this address using prime probe. This is known. So this component can easily be found out. Now here is the thing, if we can control X, right? So let us say X is controllable, it's an input or something, right? Or, you know, X varies so much and we know what is X, that it is giving us a lot of data. So let's assume for the case of simplicity that we can control X. So you can control X and then we can set it anything from minus infinity to plus infinity. Then pretty much, since we are getting the contents of array 2X, which is nothing but the memory address would be array 2 base plus X, right? So you are getting the contents of this. So you are getting the contents of this and you can set X. Then essentially you can get the content of any location in memory. You can get the content of the entire memory, which means that all passwords, private keys, public keys, credit card numbers, everything is accessible to you if in this case the value of X can be controlled and you can use this, you can kind of destructively interfere into the branch predictor such that this branch is wrongly predicted and then it goes ahead and speculatively accesses this address, and then using the trick that X can be controlled, you can pretty much access any memory location as per this formula and you can extract any data that you want, because in this case the address that you are accessing is actually containing the memory location, right? So the contents of the memory location is a part of the address that you are accessing, and this address can be found out using prime probe. So the key point is that the prime probe attack finds an address, but if that address is generated based on some data, essentially you are revealing this data, all right? And so essentially this data is what you are revealing, and as you can see, it's quite easy to mount this attack as long as I said, you have some controllability or visibility into X. Then essentially the contents of the data contents of memory are going to get leaked quite easily, of course via an address, but the address was generated on the basis of data which you can now see. So this class of executions are quite, this class of attacks are quite powerful, and most modern processors have some checks and balances against such kind of attacks. So what are the countermeasures? So the countermeasure for the first class of attacks, prime probe and so on, is that you strictly partition the resources such as cache sets between processes. So no process can destructively interfere with another. So this is a criteria. This is one of our basic criteria where we said that destructive interference is not allowed. So if that is not allowed, then one process possibly cannot affect another process. So you can't, so there is no side channel. So of course, if you do it, then your system will become inefficient, resources will be used suboptimally, but you don't have a choice. The other is that you deliberately add some noise. In a sense, go and access a few dummy addresses and so on, and so on. It will cause a slowdown. but it may make it harder, make the job of the attacker much harder. Before you ask the obvious, why don't you turn off the timer? Well, the timer is there for a reason, right? It's useful. It's useful for device drivers, network cards, games. So turning it off is not practical, but kind of capping the side channel is more practical. So with your author, I've been involved in some information theory based work where it has been shown theoretically that there are limits to what you can achieve in the form of a countermeasure. And for timing based countermeasures, the only realistic option is that you kind of assume that your hardware, if it knows that it's accessing a secure region, at least for the addresses of any great interest, you basically declare those certain addresses to be sensitive and essentially assume that all of them are amiss, in the sense that if the maximum time to access any such address is, let's say, n cycles, then all the sensitive addresses, which would be all the addresses in that cache line, for instance, should take n cycles to access. It will slow down things, but it will cut off a side channel. So finally, this is the best slide, that is the slide that we love to look at, is the conclusion slide. So we talked a lot about encryption, block ciphers, stream ciphers, counter mode encryption, the most relevant mode for here. Authenticity, confidentiality, integrity, freshness, the ASIF guarantees. Then, of course, the way SGX works, the Merkle trees, how we create, destroy, work with enclaves. And finally, this exciting and intriguing area of side channel attacks, whereby seeing just some indirect facet of the execution, you can actually figure out a lot of information, including the value of, let's say, a private key which you are trying to protect.